What's going on, math people? We're back and we're talking about limits at infinity. Okay, so just for a quick little refresher, we know that the infinity symbol looked like a sideways 8, and we know that limits are talking about y values, how far up or down a function will go approach when you're moving along the x-axis. All right, let's jump straight into this thing. Let's toss up us a handy dandy graph. All right, let's go ahead and toss up this quick little Cartesian plane. And let's say we have the function. Let's just toss up. Our famous reciprocal function. The famous reciprocal function. Alright. Alright, so as we approach 0, we know that this function is the reciprocal function f of x 1 over x. And let's say we want to approach 0 from the left. Alright, so we have the reciprocal function from the left, limit as x approaches 0 from the left for 1 over x. Alright, so we're going to bring out our handy dandy highlighter coming from the left of 0 on the function. What's happening? I thought I told you that it won't stop. That tells us the limit for this function coming from the left is going up forever and ever and ever equals positive infinity. All right, so what about when we approach 0 from the right? Approaching 0 from the right, we'll run the same thing. Let us limit as x approaches 0 from the right for the function. Toss in our highlighter, coming from the right, hop on the function, go towards 0. And what's going on? It's not gonna stop. That's right. So that means that coming from the right, the function is approaching negative infinity. So a function can approach positive or negative infinity. All right. Now, let's just toss in some information about bigger numbers and little numbers. Let's say, let's just move forward and let me get some eraser action going on because I don't need for this thing to keep going. Let's move that on out the way. All right, let's toss in when the function itself is, well, when the x value itself is approaching infinity. So let's look at something like this, right? I want you to look at this. We have 1 over 1. The denominator is 1. The value is equal to 1. When the denominator is 2, the value is equal to 0.5. When the denominator is 3, the value equals 0.333 rip it. And then when it's 4, 0.25. I hope y'all catch the picture. If we toss our denominator, as the denominator gets larger, the overall value of this statement is getting smaller and smaller and smaller. And it's going to keep going. And as the denominator approaches infinity, this value is approaching 0. All right, so got you one even better. Let's toss in the smooth calculator. All right, let's say we have a denominator of 500. Can you give me a decimal, please? Thank you. And what if we do 500,000? And what do we get there? I hope you can see that we're approaching 0 rather quickly. And I'm showing all this information strictly because I want you to see whenever you have the limit of a function where as x approaches infinity and you have x in your denominator, that is going to approach 0. All right, and it doesn't even have to be 1 in the numerator. It could be any number. It could be any number. It could be 500. It could be 700,000. If you have x in the denominator and x is approaching infinity of any number, it doesn't matter. It's always going to have a limit of 0. Now, let's pull some smoothness from Precal, right? Some degree information from Precal. All right, so recall that if the numerator degree is less than the denominator degree, n is for numerator, d is for denominator, then if this is the case, and let's just write it more mathy so that we look good. Let's say that m represents numerator degree and n represents denominator degree. All right, so so that we don't cause any confusion. All right, we know that m represents numerator, n represents denominator. Let's get rid of this right here. Now, if m is less than n, if the numerator degree is less than denominator degree, then the limit as x approaches infinity. Oh, that's an ugly limit symbol. Is 0. Let's toss in an example in between, because we have 3 of these, right? All right, so example in between, toss in some blue for example. So example, let's say we have the limit as x approaches infinity of, let's say we have 7x to the 5th minus 9x squared plus 10 all over 19x to the 21st minus 15. All right, so this is going to make your life so much easier because just recalling this information. All right, so identify the numerator degree. numerator degree, and the degree is identified by the exponent with the highest power. So we have m equals 5. The denominator degree, n equals 21. So m is less than 5. M is less than n. Therefore, the solution, baby, I just saved you a world of pain. Your solution is 0. All right. Now, what textbook and all this other stuff would tell you to do would be to divide every single term by the variable containing the highest power and then rush all of those to 0. I'm going to go through this process one time just so I can show you the madness that I just saved you from. All right, so we have the limit, and this is the madness. I'm just going to write this on the side right here. The madness that I saved you from. All right. It's good in its own place, but I like to try to get you there, okay? I'm trying to take you there, all right? So it's x, that should be blue. All right, as x goes to infinity, and this is what the textbook would say. Take this term, the variable with the highest power is 21. So we'll have this over 21, x to the 21. And the same thing for every last term. Every last term. Every last one of them. Not just the numerator. Every last one of them. And then is what you'll do is it'll apply that rule that I showed you earlier. All right, that variable, it has a greater power in the denominator for each of these. So all of these are being rushed to 0. Everything's being rushed to 0 except for that one component. And then you would have ended up with the 0 over 19, and your final solution would be 0. But if you just recall those simple steps, like let me check these degrees right quick, and then boom, my numerator degree is less than my denominator degree. 0. But keep in mind that's for when the x value is going to infinity. That is when you use this. That is number 1 of the recalling. Number 2 of the recalling. If the numerator degree equals the denominator degree, then the limit as x approaches infinity is the ratio of leading coefficients. See, you want to have these little nuggets right here in your pocket. Let's pull in the example to make this make sense. All right. So, example. Let's say we have the limit. Find the limit as x approaches infinity of, let's say, 50x to the third minus 25x to the second plus 2 over, give me something like, let's say, say 10x to the third minus 97x plus 700. Again, go ahead and identify the numerator degree equals 3. The denominator degree equals 3. All right. So we identify the numerator degree. Numerator degree. Let me toss this in on a quick highlight. Identify right there. That's where we got that 3 from. Okay. The denominator degree went to the denominator, went to the variable with the highest power. Oh, that was not supposed to do that. That was supposed to do a quick change up. And that's where we got that 3 from. Okay. Now, according to the rule that we recall from precalculus, the solution is equal to the leading coefficients. You look at the coefficients of those variables. 50 over 10, solution 5. Or you could have went through the madness and you would have still ended up going to 5. All right, so let's look at a crazy example, an even crazier example that we can toss in there. Because I want to make sure you're flowing with the flow, okay? Let's say we have something like, we have the limit as x approaches infinity of the cube root of 3 plus 16x squared over x squared plus 3. All right. And so here's where things get crazy. All right. So I don't want you to forget about the cube root. I don't want you to forget about it. I just want you to put it on the back burner for right now. Let's go inside of this cube root and the degrees inside of that cube root. Going inside of the cube root, that degree inside there is 2 for the numerator, and inside for the denominator, the degree is 2. All right, so now what I want you to do is use the same rule. All right, take the coefficient of the insides. We have 16 over 1, right? And now toss that cube root over that guy. And my Lord, I did not mean to say cube root. I meant to say fourth root. This guy is tripping. I was about to make a mess. All right, let me go ahead and get us a little handy dandy action. Get rid of that. Get rid of that. 4, fourth root. So the final answer for your limit is equal to the fourth root of 16 is 2 over the fourth root of 1, which is 1. Final answer is 2. See, saving your life. That's what I do, okay? And finally, the third thing to recall from your recollection is if the numerator degree is greater than the denominator degree, then the limit as x approaches infinity is infinity. And that infinity can be a dependency because it can go to positive infinity or it can go to negative infinity. It's just some things you have to consider. All right. So let's say we have something like example. Let's say we have the limit as x approaches infinity of 7x to the 5th over 2x squared minus 9x plus 21. All right, we have m equals 5, n equal 2, numerator degree, it's greater than denominator degree, so the limit is equal to infinity. Let's say we had the exact same example, but the problem said the limit as x approaches negative infinity of 7x to the 5th, 7x squared minus 9x plus 21, blah, blah, blah. All right. Now, what I would say is look at those exponents and make yourself a quick little. All right. If we take the difference in the exponents, the difference in those exponents, 5 minus 2, the difference in the exponents is 3. This is side to work. All right. Now, 3 is odd. When you raise a negative to an odd power, you're going to end up with a negative. So your limit will go to negative infinity. All right. And that negative infinity, that infinity should have been right there. All right. And my final thing for this video, before we get out of here, is we got to make sure we know how to work with some of these trig functions. So, just a little recalling. Sine and cosine the range of these functions depends on the amplitude. All right. And the amplitude is just simply the a that appears in front of those functions. So if that a is a 5, a 10, a 50, the highest and lowest it'll go, for the most part, is that value of a to the plus or minus of that value of a. And if there's a vertical shift, that value can change or whatever. But that range is never going to be greater than infinity. Okay? It will always be a finite number. All right? So if you have, I said all that to say, if you slide some trig equation into the mix, and let's say we want to find a limit as x goes to infinity of, let's say we have something like sine of 75x over 15x sine, that this numerator, this value is going to be stuck. Look at the amplitude. The amplitude of that value in the numerator, the amplitude is 1. All right, a should be right there, right here. If there's no value present, it's because the amplitude is 1. So essentially what you have there is something that is less than or equal to the limit of 1 over which is 0. Alright? So, I hope this puts you on game, saved you a world of headache, and until next time, my math people,